En punto.
En punto. Sí, si me dirijo a ti todo el rato, no es nada personal. Voy a ver el campo de visión de la cámara. Vale, o sea, para que se me vea tengo que estar arriba. Vale.
Hablando de los hijos que tienen y los mayores. Bueno,
No tengo prisa.
Esto es asymptotic. Asymptotic?
Asymptotic.
Asymptotic, because I don't know what is it.
Asymptotic es cuando
tienes
you have a curve. You have a curve.
Yeah.
The line which is almost tangent is asymptotic.
So,
Okay.
I have to
It's a type of sources of stars. Everywhere stars.
Because I was thinking asymptomatic. Pero claro, the asymptotic in terms of distribution. And you were at Hamburger.
Stenvata. Hamburg Stenvata. Observatory. Hamburg Observatory.
Pero bastante en
Sí,
Bueno, ahí sí, ya.
Hello. Okay.
¿Qué de César?
So we have our room at Zoom and we'll start the seminar.
Don't worry.
Okay, good morning. So today we have Francisco Jimenez, Fran, and he's going to kickstart a series of seminars in commemoration of the 20th anniversary of the Spanish Virtual Observatory. So Fran is an astrophysicist. He graduated at Complutense University, and he did his PhD in asymptotic giant branch stars at ESA. So he did 2 postdocs, one at Hamburger Observatory and the second at the National Astronomical Observatory in Spain. And then he incorporated to the Spanish Virtual Observatory group at CAP in 2008. So Fran is an expert in the virtual observatory and the scientific exploitation of astronomical archives and databases. And his current research is focused on two main topics: asymptotic giant branch and white dwarf stars, always under the umbrella of the Virtual Observatory. So thank you.
Thank you very much. So thank you for coming. As she has said, today we start a series of lectures about the Virtual Observatory and the science that the Spanish Virtual Observatory group developed under the umbrella of the Virtual Observatory. So as I had the pleasure to be the first in this series of talks, I'm going to dedicate a few minutes to explain a little bit what is the Virtual Observatory and our group, the Spanish Virtual Observatory, especially for those which are not astronomers. So the Virtual Observatory actually is an international initiative that was created in the context of the big data. You know that from decades has been many different telescopes, surveys from ground, from space that has collected huge amount of data. All these data are stored in archives, different archives, in different places, with different structures, and the way to access the data was not always as friendly and as useful as should be, or the astronomers want to be. So in 2022, was created the International Virtual Observatory Alliance, which is an international initiative that with many different groups here from different nationalities. Actually, the Spanish Virtual Observatory group is part of this alliance, and the idea is to coordinate all this the work always in the direction of the FAIR principle. The FAIR principle is that we want that all the data should be findable, accessible, interoperable, and reusable. Okay, this is the idea. So we have thousands of different archives with many different types of data, and we want to be able to use all of them in an easy way. Okay, in a transparent way for the users, for the astronomer. Okay. So the Spanish Virtual Observatory group actually started 20 years ago. It's in 2004. Start with the idea of coordinate the Virtual Observatory initiative in Spain. Okay, currently there are 22 people in the group. The PI is Enrique Solano, one member of the working here in this house in the Astrobiology Center. The main core is also people working here. 8 of us are working at the CAP. But there are people from many other institutions, from different universities, from the Complutense, from the Observatorio Astronomico Nacional, INAF in Italy, from different places. Okay, so the group is larger than only the people who are working here at the Astrobiology Center. So actually, we work in 4 different lines. The first lines that we can mention is the archive and catalogs. We create different archives. We manage different archives. Probably the most famous archive is the GTC archive or Calaralto, but there are many other archives that we have created and catalogs, which are all of them are publicly available at the Virtual Observatory, the Spanish Virtual Observatory page. The second line of work is the development of tools and services. Okay, probably both sides for those which are astronomers, for sure know VOSA. VOSA is a tool to build and analyze spectral energy distributions using public data, public photometric data, public models, okay, to analyze the source. It's able to work with thousands of sources at once. Other service is the filter profile service, which is the largest collection of filters profiles in the world. Has or can provide the response of the more than 10,000 filters from many telescopes, from space observatories, even for some missions or some satellites dedicated to observe the Earth. Okay, not only for astronomy. This is the largest collection that is publicly available so far. But this is just two of them, two examples, but there are many other tools that are also public, has been developed by the group and are published for the astronomers. Another line of work is the school, the education and outreach. So we regularly have virtual observatory schools to teach the new astronomers and also senior astronomers that want to know about the virtual observatory, the different tools that are available, how to manage with the data, how to reach the scientific results. Okay, always using science cases, real science cases, which to be using with the different tools. Okay, and finally, we made bioscience, virtual observatory science. That's what this is: science focused on the exploitation of archives and using the virtual observatory methodologies. Okay, so we use all the data available, all the data that we need to study many different lines. So this is, here I have put the main lines that we are now involved, but there are many others that we have actually researched in the past, and we are also collaborating, small collaborations in other lines, but from end dwarfs, the transient sky, low mass star, AGB star, white dwarf, binary stars, in planetary nebulae, or stellar evolution with radio data. Is just to say the main one. Okay, so as I have said, this is the first of one of the first lecture of this series of I think there are 7, 8 different lectures, different talks to commemorate the 20th anniversary, and just to say the center, what is the research that this group is doing, and to provide the main results that we have. Okay, I think it's one per month, has been scheduled one per month. Okay. So after this small introductions about the virtual observatory and our group, what I'm going to talk is about studies of white dwarf stars using the virtual observatory. Okay, and focus on Gaia data. I will explain at the time about Gaia a little bit, also about Gaia, just in case you don't know. Okay, so this is a collaboration, not only with people of the Spanish Virtual Observatory. Yeah, have the name of the people of the Spanish Virtual Observatory, but also with people which is in other institutions, in this case with Alberto Rabasa Mansergas y Santiago Torres at the Universidad Politécnica de Cataluña. Okay. So, what is a white dwarf? A white dwarf actually is the remnant of the majority of the stars in our galaxy. After the life of the stars with less than 10 solar masses ends as a white dwarf. Okay, so they are the dead body of the star. Okay, there is no more nuclear reaction, and the star is just cooling down. Okay. The size of the star is very small. This is a very compact object. Actually, the typical mass is about 0.6 solar masses, but concentrated in the size of our planet. So it has a really high density, a high gravity. Okay, and the structure is we have a electron degenerated core. Depending on the mass of the white dwarf, or the mass of the core is made of just helium, or carbon oxygen, or oxygen neon. And there is two thin layers, which is the atmosphere of the star. One thin layer made by helium, and another even thinner layer, which is above this helium layer, made by hydrogen. Okay? So it's more or less very simple structure for a star. So the spectral classification of the stars is we have two main groups. We can say that there are the DAs, are those which has these hydrogen-rich atmospheres, so present hydrogen lines in the spectra. They are called DAs. Yeah, 80% of the white dwarfs are DAs, and the non-DAs, the other 20%. Among these non-DAs, there are many different types. The types. There are most of them are those that present helium lines in the neutral helium lines in the atmosphere. They are called DBs, which is the 60%, and the other 4% is made by hotter helium-rich atmosphere white dwarf, which are the DO. DC are those that present no spectral lines in the spectra. Only we can see only the continuum spectra. The Qs present carbon lines or metal lines, the DC. These are very interesting. The DC are very interesting white dwarfs because as the gravity is so strong, any heavy element, any heavy atoms in the atmosphere very fast just go down into the stellar interior. So if we are able to detect these metallic atoms in the atmosphere of the star, it's because the material has been accreted recently. So the material is from outside the star, probably from a debris disk that we think the remnants of a previous planet or planetary systems. These are very interesting sources, the DC. Okay, so what you study the white dwarf? They retain they are very old sources, so we can learn a lot about the history of the galaxy, or the luminosity function, about the different population in our galaxy, the thin and thick disk, the halo. Also in cluster, they provide another way to estimate age for the cluster. Also to study the cooling process, can test the standard physics, okay, with variation of the gravitational constant or exotic particles, and also the DCs, white dwarf, that actually can provide hints about the formation, evolution, and survival of planetary systems. So many reasons to study white dwarf. Okay, Gaia. Gaia is a space mission led by ESA. It's an optical telescope that is surveying the sky. Was launched 10 years ago, and the end of the mission is in few months, actually, in January of the next year. And the goal of the mission is to provide astrometry, photometry, and low-resolution spectra for 2 billion sources. So Gaia is creating the largest 3D map of our galaxy, providing parallaxes, okay? So distances to the sources. Something that is really new and has provided a new window into astrophysics. Gaia is very interesting. So along the times, the DPAC consortium, which is the consortium dedicated to reduce the data, has provided different data release. Now, currently, we are in the data release 3. So we have coordinates and parallax and proper motion for 3.5 billion sources. Also, we have photometry, the G-band, which is here. We have, what is the, no, here. This is the G-band filter that cover the optical, the whole optical. It's a very wide filter. This is the G-band, but all the Gaia has also another 2 filters. This one is the VP, in the red colors is the VP. It's covering the blue part of the optical, the bluer part of the optical, and the green one is the RP, covering the redder part of the optical wavelength range. Okay. Also has provide epoch photometry, which we normally known as the life curves of 10 million variable stars. And spectroscopy. We have spectroscopy, low resolution spectra for more than 200 million sources. Okay. Also some radial velocity spectra and radial velocity measurements for several million of sources. In my work, I'm interested so far in the astrometry, the position of the sources, the parallaxes, the distance, and often with the distance we can estimate the absolute magnitude of the sources and the luminosity, and the proper motion, which is very important. White dwarf, I have said, has very small sources, so they are intrinsically faint sources. The white dwarf that we are able to detect are in the solar neighborhood. Okay? So they are close to us. That means that the proper motion is high. If we have a source with high proper motion and we want to cross-correlate the Gaia catalog with other catalogs, we need to correct the position of the source into the epoch of the other catalog. So to have the proper motion is also important in this study. We use the photometry, the 3 photometry bands, and the low resolution spectrum. Okay. Here we have an example of the low resolution Gaia spectra of a supernova. Okay, so why do you use Gaia and SVO? I have said Gaia has provided astrometry photometry that is able to distinguish the white dwarf among other stars. Just in a Helmholtz-Russell diagram like this, we can, using the absolute magnitude and the color, we can distinguish between the mean sequence or the red branch and the white dwarf. It's very easy to distinguish white dwarf among other stars because we have the distance to the stars. So Gaia has provided or has enlarged the number of sources known in more than 12 times. It could be even more in the following releases, data releases. Before Gaia, there were only known about 30,000 white dwarfs, identified by spectra by spectra. Was the way to actually identify the white dwarf. Now we have more than 300,000 sources. Okay, only in the 100 parsecs volume we have 12,000. The 100 parsec volume is one of the main important samples because it's almost complete. The previous almost complete sample of white dwarf was just in the 10, maybe 20 parsecs. Now we have almost complete volume sample at 100 parsecs. So the statistics have increased a lot. We have low resolution spectra for 100,000 sources, which is the largest database of spectra for white dwarf. Okay? But in order to study these sources, we need to characterize the sources. And here is the virtual observatory that start to play. With the virtual observatory, we can access in an easy way to multi-wavelength photometry. So we can create the SED distribution and obtain the observed flux and then the luminosity. We can obtain the physical parameters, the temperature, the mass of the sources. And we have tools able to work with thousands of sources at once. So it's the best match, Gaia and virtual observatory. Okay, it's a very good pairing. Okay, so I have divided the work that we have done since we have been working in white dwarf since the second data release in 2018, and this is I have divided different works in 3 blocks. Okay, so first is the identification and classification, then studies of galactic and white dwarf population, and studies of peculiar sources. So I remember the day of the data release, the second data release. I remember that the ESA released the data at 12 at the noon, and I was at my office. My office is at the ESA campus. There was a big party in the ESA campus with this release, and I was sitting at my office in front of the computer. Just at 12, I click and send my query to the archive. In 5 minutes, I got the data, sharing with all my colleagues to start working on this. So we were able to publish the first catalog of white dwarf based on Gaia data. I told you that before Gaia, there was about 30,000 known white dwarf. We were able to identify more than 70,000 white dwarf. Okay? The selection made on the HIR diagram. Of course, there was a lot of contamination that we need to clean, but it was the first one. Using the VO, we enhanced the catalog with physical parameters. We built the SEDs of all of them and feed the SEDs with the theoretical models to obtain the different parameters. Okay? Here we see the temperature, gravity, size, and mass of the white dwarf. And the red line is the predicted distribution from the current models that was at this time. Clearly, the models were not able to reproduce the observations. So this has actually moved forward the modeling of the white dwarf. Okay. Also, probably you have heard about the bifurcation in the cooling sequence of the white dwarf. This is the cooling sequence of the white dwarf in the HIR diagram, and you can see there are a bifurcation. Is the A branch and the B branch. At the beginning, the first explanation was okay. The A branch is the hydrogen-rich atmospheres, the DAs. The B branch is the helium-rich atmospheres, the DBs. We look in detail on this, and we say, no, this discrepancy is not able to explain this. Later, there has been other works, theoretical works, that have been able to explain. And the most plausible explanation is that the BDs is we need a mixed models with helium and carbon contribution. So, but there is an open question yet. Still an open question. Okay, then with the data release 3 appear the spectra. In the data release 2, there was no the low resolution spectra available, but with the data release 3, we have the low resolution spectra. So we use the low resolution spectra to express a spectra classification of the white dwarf. And another two works. So the first thing that we were able to use with the data release 3, which is based on a longer observation time, we have better parallax, better proper motion. We were able to refine the catalog, especially in the redder part, in the less luminous part of the sequence. So we increase the number of sources. And here we have a comparison of the SED made by photometric data from the virtual observatory, and here we have the photometric data obtained, is the synthetic photometry obtained from the Gaia spectra. So we can see that the coverage of the SED is much better, and we can even distinguish the different spectral lines clearly. So we took the Gaia spectra, and we obtained the synthetic photometry of the GPass filter system, which is a filter system with 56 narrow bands filters. So at the end, you have a pseudo spectra with the same resolution of the Gaia spectra, but with photometry. And we can put this photometry into BOSA and work with BOSA. Okay, using a very simple method, we are able to classify the white dwarf between DA or non-DA, depending of which models fits better to the observations. Okay, and then we look more in detail in the bifurcation, and we were able even to give percentage of number of sources which are in the different branches. In the A branch, most of them are DA, but there are some non-DAs. And also, and in the B branch, we have that most of them are non-DAs, but there is a large percent, almost 1/3 of them are DAs. So this should be explained. So we open this question, and still, from my best knowledge, has not been a clear answer of this. And also, we were able to study the different distribution of the temperature and the mass with a clear separation between DAs and non-DAs. The first time we have so many sources. Okay, so we have increased the statistics a lot. Okay, finally, we were able to study the spectral evolution of the white dwarf with the largest sample so far, with 34,000 white dwarfs. The spectral evolution is the rate, the percent of non-DAs with respect to the total number of white dwarfs, and the evolution with the temperature. How this percent change with the temperature. Okay, the black is our work. Okay, there was many other works, but with less number of sources, and now we were able to create the most firm spectral evolution for these sources. Okay, so let's go to the second block of studies. Now we study galactic populations of white dwarfs. Okay, for this we use artificial intelligence technique and a robust synthetic code, population synthetic code. Of course, with the virtual observatory and the gathered data. And in this case, we were able to, using the synthetic code, we were able to, we trained the random forest and then apply the random forest into the real data. And this is the result that we obtained. We were able to, we were able to separate the sources between the thin, the thick, and the hollow stars. And this is the percent that we obtained. And another study that we did was binary systems. Okay, we studied the binary population of white dwarfs. Okay, both resolved and unresolved population. So for the resolved populations, when the two sources are identified by Gaia separately, okay, we have the distance and the proper motion of both sources. Then, using a very simple method, just comparing the physical separation of the sources. We have the distance and the angular separation. We have the true physical separation. And with the proper motion, we have the tangential velocity of the source. We can estimate the different tangential velocity. And here you can see clearly that the sources cluster in two groups. The line which is here is the maximum difference of tangential velocity for the most extreme binary, which is the most massive binary for a white dwarf, 1.4 solar masses, and the most massive star in the solar neighborhood. We did this study in the 100% volume. And this is the line. The line clearly split the sample in two. We have the true system and the fake one. So we are able to identify the binary systems. Okay. And with this, also we study the properties of the different binary systems. We estimate the rate of binarity for this, which is very important for galactic studies. So on. Okay. And now unresolved, the system that Gaia has not been observed separately. They are too close in the sky to be able to be resolved by Gaia. Okay. In this case, which is the methodology that we use, we identify composed SEDs. Here, the red dots are the observations. It's clear this is not a typical SED with a single object SED with a peak and then the fade down at longer wavelengths. And we fit this the observational data, the red one, with two models. One for a white dwarf, which is the cyan one, and the purple is for a mean sequence star. So we were able to identify the samples and also to study the characteristics of the sources, the luminosity, the temperature. We can obtain the physical parameters for both of them. Okay, so another exercise that we did. And now the third block of the third line is to identify peculiar white dwarfs. In this case, we are focused on white dwarf with infrared excess. So in infrared excess, that means showing more infrared emission than predicted by the model. And this is an indication of a circumstellar material or a substellar companion, okay, a brown dwarf. So in the first case, we study using the Gaia DR2, actually. We create the SEDs and we identify, here in blue is the model, we identify those white dwarfs with X-tex emission. And actually, we identify 77 white dwarfs with infrared X-tex. 42 were unknown, previously unknown. So it was we increased the number of known white dwarfs with infrared X-tex. Okay, a lot. Now that we have the third release, we have the Gaia spectra. So we are improving or extending the study using the DR3, that we have better parallax, better proper motion. So when cross-matching the Gaia counterpart with infrared catalogs, we can move the white dwarf into the position of the infrared catalog, some of them that has more than 20 years old. So this is very important. And again, we have, here is the optical part, which is populated by the Gaia spectra using the GPAS filters. And here is the photometric data. So we can see how the blue dots are the models, and there is an X-tex here. Here we have the fit of this SED using a 10,000 Kelvin white dwarf model and a 1,200 Kelvin superstellar companion model. Okay, so this is this work is on progress. Raquel Murillo is now working on this. Is doing the PhD on this, and I can say that we are going to multiply the number by a factor 4 or even more, the number of known sources, which is very interesting. And of course, when we detect an interesting source, we have actually made the follow-up observation of most of the 77 identified sources with the Gaia DR2. We have the spectra from the BLT or from the GTC, and we have identified the first inner system made by a brown dwarf and a white dwarf, which is an unresolved system, and there is a third object, another white dwarf, which is part of the system. So it's a triple system. Very interesting system. Okay. Just to finish with, just to say you that all of these catalogs that we have created, catalogs with enhanced catalogs, because it's not only the source, but also the parameters, the physical parameters of the sources obtained from the virtual observatory, are publicly available in the Spanish Virtual Observatory archive. So here you can access the archive created with a white dwarf, but there are many other archives with should dwarf, with binaries in the web page, just to be used for the community. So just finally, in conclusion, Gaia and Virtual Observatory has demonstrated to be a really powerful pairing that provide a lot of good results with a reasonable effort. That the collaboration is use this synergy in combination with the artificial intelligence technique. We are now applying artificial intelligence technique to try to separate the known DAs. Remember the known DAs were the DBs, the DO, the DC, DQ, DZ. So we are trying to classify these sources using artificial intelligence. And in the future is too wide to be actually to be able to work on all the ideas that appear all the time. But one of the ideas that was Ricardo Rizzo that actually came several months ago was to exploit the ALMA archive, to use the ALMA archive to study white dwarf, to identify the white dwarf with emission of this wavelengths that actually will be a hint of a substellar companion of circumstellar material. Also, when they use other spectroscopic surveys, okay, that will be out of them, include more models, more updated models into BOSA to refine the work and apply artificial intelligence techniques on all of this. So the future is really promising, and a lot of work is waiting for us. Like this, thank you very much for your attention. Time for questions.
Oh, thank you. Thank you, Francisco. So yeah, we have time for a few questions or comments. Yep.
I was just curious on your last future work point, the point on the future work. Can you say a little bit more about the ALMA part? What would be, I'm not a stellar astrophysicist, so what would that add? And what's the significance of that?
Could you repeat?
Can you say a bit more about the ALMA exploitation of ALMA archive?
Well, I have said we are just for the moment we are identifying the white dot that has been observed by ALMA, just because there is a program focused on this, on observing the white dwarf of just serendipity, because it was on the field of view, and identifying which of them has emission as a punctual source on the position of the white dwarf, and from here we have to continue. We have actually also maybe to apply for observing time to cover the spectral distribution in the radio wavelengths and continue from this. Maybe Ricardo want to say something more. It's his idea. His line of work.
Just to give in more detail, we mine the France catalog of 20,000 white dwarf within 100 parsecs of distance, and found in the ALMA archive, and found that it was observed in some hundreds or stars, and we search for extender measure or point sources in all those thousands, hundreds of cases, and tentatively found some point sources close or very close to the star. We are starting analyzing that case, but in some cases, I don't know if in most cases or in a few cases, this may be sub-millimeter galaxies. So we can confuse them. So we have to learn a lot about that. It is possible. It's possible, but by chance may be projected there. So that's why we need to analyze in more detail, because in these cases we have only one wavelength detection at one frequency. In at least one case, we found the source very close to the close within the astrometry precision of the ALMA archive. We found the point source very, very close to the white dwarf, and its flux does not fit with the ECD of the star itself. So it's a promising case.
Any more?
Does the virtual observatory have any radio maps or radio spectra?
Radio data is actually the big missing in the virtual observatory. It looked like all questions are for Ricardo, not for me. He's working on this. There are radio maps available, the radio surveys. There are something, but not in the. Of course, there is not the coverage that we have in the optical or the infrared. But there are radio data. There are radio data.
Okay, thank you. Thank you for the talk.
Thanks for the talk. I was wondering whether the DA and non-DA white dwarfs, do they live in different environments that could explain the different composition of the atmospheres, or is it something that is complicated to study?
This is something that we need to answer. What is the origin of the different white sun, white dwarf present the two layers? Others has no this second layer, this hadron layer above the helium layer. So, to my best knowledge, there is not a good answer for this. Something that we have to work on. Because actually, until now, there was a very few, there was not too much white dwarf, and the study was really hard because you need actually to identify each white dwarf by a spectroscopy one by one. But statistical studies, we are starting to do these statistical studies.
Okay. Thank you.
So any more questions here? And let's assume no. So we'll close it. Thank you so much, Francisco, and it was a pleasure.
Welcome.